Viviani's still on his wheel. They're still going to come round the corner. Greipel's there. Can he hold it? But Viviani's coming round him again. Viviani is there. But it looks as though Greipel, I think, has it. We'll take a look at the photo. It's so tense. It's so tight. Nobody's celebrating. But it looks as though Andre Greipel may well have just got it from Elia Viviani. We'll have to have another look.
See Greipel going. Viviani again chooses the shorter line. Who's got it on the line?
Oof. Well, oof. You know, it might be Viviani again.
Very, very close. That is another photo. But look how late Viviani left it. Great timing. Was it enough? Again, Greipel drifted from that
angle. I'm saying Greipel. From the other, I'm saying Viviani. This should tell us. Ooh. Well, it should have told us.
Blimey, I tell you what, that was so close, so exciting.
Here's the photo finish. Greipel in the red, Viviani in the black. Well, from that to me, from that to me, you can see a bit of Viviani's wheel to the left of the black line.
We're talking with millimeters here, you know, 1 or 2 millimeter. I mean, very, very close. Thrilling finale.
Hey there, cyclist. Welcome to the sport of cycling. You may have been watching the Tour de France, or another Grand Tour, and now you want to be like some of the many men, women, and children who have gotten into the world of cycling. As you get into this sport, there are a couple of key ideas you really need to understand, such as bike safety, gears and shifting, and drafting. Today's video lecture will help you understand drafting, what it is, and why it's so important to those who cycle. Drafting is when one or more riders follow closely behind a lead rider to reduce drag, as seen in the picture here. This is taken to an extreme when many riders do it together in what is called the peloton. A peloton is a main group of riders generally formed in a cycling race. As seen here, the peloton in races like the Tour de France can include over 100 riders. Now, I know what you're thinking. Isn't this a little bit dangerous? Well, yes, if you aren't being careful, drafting can be extremely dangerous. But when this strategy is used in a safe manner, the payoff is huge. Drafting can save an enormous amount of energy for those behind the lead rider. This can sometimes be the difference between first and second place. Now, to understand why drafting works so well, we have to have an understanding of some important aerodynamic principles.
In the free body diagram shown here, a cyclist is moved forward by the frictional forces generated when the wheels spin as you pedal. The resisting force is drag, the force you feel from the air flowing past you. The total drag is computed by two components, pressure drag and skin friction drag. Pressure drag is a force due to pressure distributions over a body surface. Pressure drag is what makes this better than this, even if they are both the same size. Skin friction drag is a force due to friction between the fluid and the surface, which is a result of fluid viscosity. The smoother the surface, the less skin friction drag that you have. For cycling, total drag is much more heavily influenced by the pressure drag, so we won't focus on skin friction drag as much. Your pressure drag is improved as a cyclist when you get into a more aerodynamic position, such as this. It is also improved when you are drafting.
The reason that drafting reduces drag is demonstrated in the following sequences of animations. In this first animation, we show the top view of a single cyclist and the airflow around him. Having to break the air in front of him and the vortices behind him results in a large pressure gradient over the cyclist's surface. A high pressure gradient will result in a high pressure drag. In the second animation, the drafting cyclist is also shown along with the lead cyclist. Notice that the lead cyclist has already broken the air when it reaches the second cyclist. Thus, a low pressure region is formed. The lower pressure in front of the drafting cyclist results in a smaller pressure gradient and pressure drag. Thus, he does not experience as much drag as the lead cyclist.
To compare drag values, we compare what is called the coefficient of drag. The coefficient of drag is calculated using the total drag felt by an object, its area, velocity, and the density of the fluid. It is helpful to compare the coefficient of drag because it lets us compare the drag no matter the size of the cyclist, whether big or small. We can find the coefficient of drag both using a computer simulation and with a wind tunnel. In this video, we will use both to show how great drafting can be. Throughout the video, we will use spheres to represent cyclists, but rest assured, by correctly matching aerodynamic parameters, our results can easily be applied to you as a cyclist.
To show the benefits of drafting, we will use a tool called StarCCM to simulate two cyclists drafting. In the computer program, we can model spheres to visualize the drop in drag coefficient when drafting. To show this, we generated two models, a single sphere and two spheres, one directly behind the other in drafting formation. The spheres are modeled with a 2-inch diameter. We then introduced a steady airflow directed at the sphere or spheres, depending upon the model, thus inducing a drag force, which can be used to calculate a drag coefficient. The first simulation will calculate the drag coefficient for a single sphere. We can use this number as a baseline number to see the decrease in drag coefficient when spheres are placed in a drafting formation. If drafting works, then we should see a significant drop in the drag coefficient for a sphere drafting off another. The results of the single sphere simulation is shown here. This image shows a plot of two different components in our analysis, the velocity profile around the sphere and the pressure gradient over the surface of the sphere. For the velocity flow around the sphere, warm colors represent higher velocities and cold color represent lower velocities. The maximum speeds are located near the top of the sphere and the lowest speeds are located behind the sphere or at the front of the sphere. For the pressure gradient, brown represents the higher pressure values while dark blue represents the lower pressure values. The highest pressure occurs at stagnation point. After running the simulation for a single sphere model, the resulting computed drag coefficient is 0.3807. As I mentioned before, we will use this number as a reference number for our double sphere simulations. Our second simulation will calculate the drag coefficient for a second sphere placed directly behind the first sphere. To test the decrease in drag coefficient, simulations were run in which the center of the second sphere was placed 4 inches from the first sphere, such that there is a 2-inch gap between the two. This means the gap between the spheres is equal to one sphere diameter. The results of the second simulation are shown here. Once again, for the velocity flow around the sphere, warm colors represent higher velocities and cold color represent lower velocities. It is important to note that the speed of the flow hitting the first sphere is much greater than the speed of the flow hitting the second sphere. For the pressure gradient, brown represents the higher pressure values, while dark blue represents the lower pressure values. To gain a better look at the drafting phenomenon, we can look at the pressure gradient in the flow around the sphere. The higher pressure values are red and the lower values are dark blue. We can see that the pressure in the flow right before the first sphere is at its greatest. However, the pressure in the flow before the second sphere is much smaller. As mentioned before, this region right in front of the second sphere is the low pressure region and is the cause of the lower pressure drag. From a front view, we can see the pressure gradient over the surface of the two spheres. The larger pressures are brown and the lower pressures are dark blue. You can see that the front sphere experiences a much greater pressure gradient over its surface in comparison to the drafting sphere. After running the simulation, the computed drag coefficient for the first sphere is 0.3646 and the drag coefficient for the second sphere is 0.2384. When we compare the results of the first and second simulation, we can see a drastic difference between the drag coefficient for the sphere by itself and the second sphere, or the drafting sphere. For our scenario, in which there is a 2-inch gap between the two spheres, the second sphere experiences a 37.3% difference in drag coefficient compared to if it was alone. This is huge for a cyclist. As a cyclist, this would make a world of difference when riding.
These computer simulation results can be validated in the wind tunnel. Wind tunnels are an important tool in aerodynamic testing because they let us blow air past an object and simulate an object moving at that speed. In this wind tunnel test, the wind blows past the sphere from right to left. The sting then measures the forces on the object. We will specifically be focusing on measuring drag, but they use the same type of setup to measure lift to make sure that airplanes don't fall out of the sky. To show how drafting works, we first put a sphere in a wind tunnel by itself, just to measure the coefficient of drag. The coefficient of drag was 0.48. This will be our reference, and we will see if it is possible to reduce the drag by drafting. To simulate drafting, we will place an identical sphere in front of our original sphere. In this way, our rear sphere is drafting off of the front sphere. With this setup, we will change the distance between the spheres and look at how the coefficient of drag changes. This will simulate one rider drafting behind another cyclist and moving closer and further from the lead cyclist. We will now perform a series of tests. Okay, here are the results. The coefficient of drag is shown on the y-axis. Remember, the smaller the number, the better. Shown on the x-axis is the separation distance. We are showing that as distance divided by radius. The dotted red line across the top is the reference coefficient of drag. This is the drag that we obtained when the sphere was in the wind tunnel all by itself. The blue dots represent all of the tests that we performed, and the dotted green line is only there to help point out the trend in the data. What you can clearly see is that drafting works. The closer the spheres were together, the less drag was felt by the rear sphere. When the spheres were really close, the rear sphere had about half of the drag that it would have had by itself.
So what does this mean for you as a cyclist? Well, everything. In both the computational and experimental analysis, we can see that drafting can make a huge difference in reducing drag. With races over hundreds of miles determined by mere seconds, drafting is an absolute necessity in the world of cycling. Racing teams are paying millions of dollars to reduce drag by a single percentage. Drafting will make it easier for you to maintain higher speeds. With less drag, you can save an enormous amount of energy, allowing you to go farther and faster. Instead of only being able to do a 20-mile bike ride, you may be able to do a 40 or 50-mile bike ride. Who knows, maybe you'll be even crazy enough to do a 100-mile bike ride. So find a buddy. Find someone who wants to ride with you and draft off each other. You'll be amazed at the results.